In 1949, a young mathematician walked into Princeton with a problem. His name was John Nash. He was 21. Economics had a hole in it. It could explain a lone buyer. It could explain a lone seller. It could explain a market with so many people that no one person mattered. But it struggled with the middle case. Two firms, three generals, five bidders, a few countries, a small set of people who could all hurt each other by moving alone. In those worlds, your best move depends on mine. Mine depends on yours. The logic starts to chase its own tail. If I lower my price, you may lower yours. If you lower yours, I may cut again. If we both cut forever, nobody knows where the analysis stops. Nash asked a clean question. Can a strategic game have a resting point? Not a moral outcome, not a fair outcome, not even a good one, a stable one. The formula was U sub I of S sub I star, S sub minus I star, is greater than or equal to U sub I of S sub I, S sub minus I star. Here, U sub I is player I's payoff. S sub I star is player I's equilibrium strategy. S sub minus I star is the other player's equilibrium strategies. S sub I is any other strategy player I could choose. For every player I, in every alternative strategy, S sub I. That inequality became the basic grammar of modern game theory. It now sits behind antitrust cases, auction design, nuclear deterrence, market entry, platform pricing, biology, political bargaining, and the way economists say the word equilibrium. The idea is simple enough to say at dinner. An outcome is stable when no one can do better by changing alone. The hard part is proving that such a point exists. That proof helped remake economics. Strategic life is not solitaire. That is the puzzle. A chess move is only good because of the reply it invites. A price cut is only good because of how rivals react. A promise is only strong if the other side believes you will keep it. In many real choices, the payoff does not come from your move alone. It comes from your move plus everyone else's move. Before Nash, game theory had a strong but narrow foundation. In 1928, John von Neumann proved the minimax theorem for two-player zero-sum games. In those games, one player wins exactly what the other loses. Poker fits part of that world. Some military conflict fits part of it too. In 1944, von Neumann and Oscar Morgenstern published Theory of Games and Economic Behavior. That book gave economics a new language for strategy. But much of life is not zero-sum. Two firms can both profit. Two countries can both lose. Two bidders can both overpay. A union and a company can both prefer agreement to a strike. The old theory did not yet have a general resting point for those worlds. The problem was not that people were irrational. The problem was that perfectly rational people could keep reacting to each other forever. That was the trap. The real problem was mutual dependence. Take a simple business case. Two coffee shops face the same street. If one shop sits near the train station, the other wants to move nearby. If both crowd the station, one may want to move toward the offices. If one moves toward the offices, the other rethinks again. Each owner asks a local question. Given where the other shop is, what should I do? That local question can create a loop. This was not a toy problem. In the 1940s, economists had many such loops. They had oligopoly pricing, they had bargaining, they had voting, they had military strategy, they had market entry. They did not yet have one general concept that named the stop point. So people used special cases. Cournot had a quantity model. Bertrand had a price model. Von Neumann had zero-sum games. Economists used diagrams. They used stories. They used case logic. Those tools helped, but each one lived in its own room. There was no general rule that said, here is what stability means when all players optimize at once. That missing rule had to do more than patch one corner case. It had to work for more than two players. It had to work when interests partly aligned. It had to work when interests clashed. It had to work even when no player could command the others. That is why the gap mattered. This was never just an academic riddle. Institutions are strategic machines. Courts ask whether firms will collude. Regulators ask whether an auction rule will invite truthful bids. Governments ask whether threats will deter war. Platforms ask whether sellers, buyers, and advertisers will stay or leave. In each case, the question is not, what should one person do? The question is, what outcome can survive everyone's incentive to move? That question still matters in 2026. It matters in chip wars. It matters in cloud pricing. It matters in ad auctions. It matters in social networks. It matters in trade policy. It matters in every market where a few players watch each other closely. A traffic jam, a price war, and a cold war can all share the same hidden shape. That is the strange part. The surface story changes. The logic underneath does not. Each side looks at the others. Each side asks, what happens if I move now? Each side knows the others ask the same thing. Without a way to name the stopping point, analysis drifts. You can tell stories forever. You can draw arrows forever. You can always say one more move might come next. Nash saw that the field did not just lack answers. It lacked a clean definition. The gap was a general definition of strategic stability. It was a point where every player is already making a best response to everyone else. That sounds small. It was not small. Once you can define the resting point, you can ask if it exists. If it exists, you can ask when it is unique. If it is not unique, you can ask which equilibrium institutions push people toward. You can begin to compare rules. You can test market designs. You can study threats and promises. You can move from clever examples to a general method. That was the opening Nash created. The next step was harder. It is one thing to say what a stable outcome means. It is another to show that strategic games can reach one at all. A game starts with a cast. There are players, there are strategies, there are payoffs. A player is a decision maker. It can be a person, it can be a firm, it can be a country, it can be a trader, it can be an algorithm, it can be a committee. A strategy is a full plan for what that player can do. A payoff is what the player gets after all choices meet. That last phrase matters. The payoff comes after choices meet. If two shops choose locations, each payoff depends on both locations. If two firms choose prices, each payoff depends on both prices. If two countries choose whether to arm or disarm, each payoff depends on both choices. Think of choosing a seat at a dinner table. Your best seat depends on where everyone else sits. Now add one more phrase, best response. A best response is the best move you can make if everyone else keeps their moves fixed. If shop B is at the train station, shop A asks where it should go. If shop A is near the offices, shop B asks whether to stay or move. Each side is not solving the whole world. Each side is answering a conditional question. Given them, what should I do? That is the engine of Nash. If every player is best responding at the same time, what does that point look like? Here's the Nash equilibrium condition. U sub I of S sub I star, S sub minus I star, is greater than or equal to U sub I of S sub I, S sub minus I star. For every player I, for every other strategy, S sub I. Here, I is the player we are checking. Here, S sub I star is player I's strategy at the proposed equilibrium. Here, S sub minus I star is the strategies of all other players at the proposed equilibrium. Here, S sub I is any other strategy player I could try. Here, U sub I is player I's payoff function. Here, greater than or equal to means at least as good as. Say it slowly. At the starred strategy profile, player I gets payoff U sub I. If every other player keeps the starred strategies, player I cannot gain by switching to any other strategy. That must be true for every player. That is the whole idea. Nobody can improve by deviating alone. It is like a group photo where everyone has found the best spot they can get without moving anyone else. Nash first proved the general result in his Princeton dissertation. It was only 28 pages long. The loop stops when each player is already making the best move against the others. Notice what the equation does not say. It does not say the outcome is kind. It does not say the outcome is efficient. It does not say the players are happy. It says only that no one has a profitable solo escape. That is why the idea is so useful. It splits stability from goodness. A traffic jam can be stable. A price war can be stable. An arms race can be stable. A bad norm can be stable. The formula gives you a test. Hold everyone else fixed. Ask one player if they would switch. If the answer is no for everyone, you have a Nash equilibrium. But why should such a point exist at all? Nash's proof turned best response into a fixed point problem. A fixed point is a point that a rule sends back to itself. Put an X. The rule gives you X again. That sounds small. It is not. Many deep results on stability have that shape. For Nash, the rule is a best response map. Start with a proposed set of strategies. Each player asks for its best response. The rule sends the old profile to a new profile. At equilibrium, the new profile is the same as the old profile. The chase stops. Imagine a thermostat. If the room is cold, the heat turns on. If the room is hot, the heat turns off. The fixed point is the temperature where the system no longer pushes away. Nash used a fixed point theorem to prove existence in finite games with mixed strategies. Mixed strategies are the key bridge. A pure strategy picks one action, a mixed strategy assigns probabilities to actions. In rock, paper, scissors, always playing rock is pure. Playing each option 1/3 of the time is mixed. The mixed strategy space is a simplex. That means the probabilities are non-negative. That means the probabilities add to 1. We can write that as P sub I is greater than or equal to 0. We can also write sum over I of P sub I equals 1. Here, P sub I is the probability assigned to action I. Here, greater than or equal to 0 means probabilities cannot be negative. Here, sum over I of P sub I equals 1 means all probabilities add to 1. We can name the whole set as delta of S sub I. Here, delta of S sub I is the simplex of player I's mixed strategies. We can also name the best response rule as BR of S. Here, BR of S is the set of best responses to strategy profile S. If you are thinking this proves existence but not how people find it, you are exactly at the wall. The pure game may cycle. Rock beats scissors, scissors beats paper, paper beats rock. There is no stable, pure choice there. But the mixed strategy space fills the gaps. Once choices become probability mixtures, the strategy space becomes compact and convex. The best response relation then has enough shape for a fixed point theorem to bite. Then the proof says that somewhere in this space, strategies and best responses fit together. That is Nash's move. He did not solve every game by hand. He proved a resting point exists. Once that concept existed, it traveled. Industrial organization used it for pricing and entry. Political science used it for voting and deterrence. Biology used it for evolutionarily stable strategies. Computer science used it for auctions and multi-agent systems. One test for stability crossed fields. If a resting point always exists, why is Nash not the end of game theory? The wall is selection. Nash proves that equilibrium can exist. It does not tell you which equilibrium people will play. Some games have one equilibrium. Many have several. That creates the equilibrium selection problem. A group can agree to meet at the north gate. A group can agree to meet at the south gate. Both are stable if everyone expects the same gate. The theory alone may not pick one. In 1965, Reinhard Selten introduced subgame perfect equilibrium because standard Nash could allow empty threats. Take an entry deterrence game. An incumbent threatens a price war if a rival enters. But once entry happens, fighting may hurt the incumbent too. The threat can be Nash in the full game. It can still fail the test of credibility. That is not a small issue. Real strategy depends on credible threats. If a threat hurts the person making it, the other side may ignore it. Nash by itself may not filter that out. There is another wall. People may not know the full payoff table. They may have private information. They may make mistakes. They may learn slowly. They may care about fairness. They may care about identity. They may care about reputation. They may care about spite. John Harsanyi extended game theory to incomplete information. Reinhard Selten refined equilibrium for dynamic games. Thomas Schelling studied focal points. Later works studied bounded rationality. Later works studied learning. Later works studied repeated games. Later works studied mechanism design. The loop stops only if players know enough, believe enough, and treat the equilibrium as the relevant resting point. Nash is base camp. It is not the summit. So what should a modern decision maker do with the formula? Nash equilibrium is not a promise that the world will be fair. Inside a strategic system, it is the cleanest first test for what can survive. The practical use is simple. When you face a strategic problem, stop asking only what you want. Ask what everyone can keep doing after everyone else reacts. That is the Nash habit. In business, it changes how you read price cuts. A price cut is not just a price cut, it is an invitation. Rivals may answer, customers may wait, suppliers may adjust. The real question is whether the new price state is stable after those replies. In investing, it changes how you read moats. A moat is not a slogan, it is a strategic equilibrium. If rivals can profit by attacking, they will. If customers can profit by leaving, they will. If the current state persists, something in the payoff table is holding it there. In policy, it changes how you read rules. A good rule does not beg people to behave. It changes incentives, so the desired behavior becomes a best response. That is why Nash became the grammar of modern strategy. It reshaped industrial organization. It changed auction design. It changed antitrust analysis. It changed bargaining theory, political science, evolutionary biology, and strategic trade theory. In 1994, Nash, Harsanyi, and Selten received the Nobel Prize in Economics. That prize marked a change. Game theory had moved from a niche mathematical field into the operating system of modern economics. The formula solved the gap from the start of this episode. It gave strategic stability a test. No player can improve by moving alone while the others stay fixed. That is not the same as good. That is not the same as just. That is not the same as efficient. But it is the first question every strategist must ask. Can this outcome survive? Tomorrow, when you analyze a competitor, write down each player's best response before you write down your own plan. If the plan only works before the other side answers, it is not strategy, it is hope. The smartest move is often not the move that looks best alone. It is the move that still looks good after everyone has answered. So remember the equation. UI of SI star and S minus I star is at least as good as UI of any other SI, holding everyone else fixed. That is Nash equilibrium. It says, stability is no profitable solo escape. It gave economics a general language for strategy. And before you call any strategy smart, ask whether it survives everyone else's best response. Nash equilibrium is not a promise that the world will be fair. Inside a strategic system, it is the cleanest first test for what can survive. The practical use is simple. When you face a strategic problem, stop asking only what you want. Ask what everyone can keep doing after everyone else reacts. That is the Nash habit. In business, it changes how you read price cuts. A price cut is not just a price cut, it is an invitation. Rivals may answer, customers may wait, suppliers may adjust. The real question is whether the new price state is stable after those replies. That shift sounds small. It is not. Most bad strategy starts with a private wish. Good strategy starts with the full board. The smartest move is often not the move that looks best alone. It is the move that still looks good after everyone has answered. In investing, it changes how you read moats. A moat is not a slogan. It is a strategic equilibrium. If rivals can profit by attacking, they will. If customers can profit by leaving, they will. If the current state persists, something in the payoff table is holding it there. That forces a harder kind of honesty. You do not ask if a firm looks strong. You ask why others have not broken its position yet. You ask what each side gets from staying put. You ask what it would take to make one side move. In policy, it changes how you read rules. A good rule does not beg people to behave. It changes incentives so the desired behavior becomes a best response. That is why this idea traveled so far. It gave economists, lawyers, and states a way to test whether a system could hold. Not whether it was noble, not whether it was fair, whether it was stable once real people pushed back. Here's the core test again. U sub I of S sub I star, S sub minus I star, is greater than or equal to U sub I of S sub I, S sub minus I star, for every player I and every other choice of S sub I. Here, U sub I is player I's payoff. S sub I star is player I's equilibrium strategy. S sub minus I star is the equilibrium strategy set of all the other players. S sub I is any other strategy player I could choose. That is the whole point in one line. No player can do better by moving alone while everyone else stays fixed. That test solved the gap at the heart of the problem. It gave strategic stability a clear rule. It told you when a pattern of choices could last, even when no one trusted anyone else. Its reach was huge. Nash equilibrium became the default way to solve non-cooperative games. It reshaped industrial organization, auction design, antitrust analysis, bargaining theory, political science, evolutionary biology, and strategic trade theory. Then came the public mark of arrival. In 1994, the Nobel Prize went to John Nash, John Harsanyi, and Reinhard Selten. That prize marked game theory's move from a niche branch of math into the working system of modern economics. You can see the stamp of it all over daily life, in spectrum auctions, in merger cases, in platform pricing, in deterrence policy, in any market where each side moves while watching the others. But the trade is plain. Nash equilibrium tells you what can persist. It does not tell you whether the outcome is good. A stable bad system is still stable. A cruel bargain can still be in equilibrium. A price war can be rational. So can silence. So can mutual harm. That is why the tool matters. It clears away hope. It clears away posture. It makes you face the incentives that keep a system where it is. Tomorrow, when you analyze a competitor, write down each player's best response before you write down your own plan. That one habit will slow you down in the right way. It will make you test your move against reaction. It will make you see that strategy is never a solo act. Nash equilibrium says U sub I of S sub I star, S sub minus I star, is at least as good as any solo switch for every player. That idea gave economics a general language for stable strategy, from auctions and antitrust to deterrence and platform markets. Before you call any strategy smart, ask whether it survives everyone else's best response.